we want to find the parametric equations for the line where the two planes intersect. To do this, we'll have to find a direction vector for the line, as well as a point on the line, which is a point on the intersection of these two planes. Before we do this, let's look at it graphically. Here we see the graph of the two planes, where this yellow vector here is a normal vector to the yellow plane, and this blue vector here is a normal vector to the blue plane. And if we find the cross product of these two normal vectors, it'll give us this gray vector here, which is orthogonal to both normal vectors, but notice how it's also in the direction of the line of intersection. So the cross product of these two normal vectors will give us a direction vector for the line, and then we'll find a point in this line of intersection, which will allow us to then write the parametric equations for this line. So let's go back and set this up. We know from the point normal form of an equation of a plane that the coefficients of x, y, and z give us the components of a normal vector to the plane. So looking at this first plane, notice how a normal vector, we'll call it vector n sub 1, would have an x component of 13, a y component of 3, and a z component of -6. Then looking at the second plane, it would have a normal vector of, let's say, vector n sub 2, which would have an x component of 10, a y component of -9, and a z component of -3. So now we have two steps. Number one, we'll find a direction vector of the line of intersection by determining the cross product of these two normal vectors. So we'll find vector d for a direction vector, which is equal to the cross product of the two normal vectors. And because we found several cross products already, I've already found the cross product ends up being the vector with an x component of -63, comma, a y component of -21, comma, and a z component of -147. Now we can use any scalar multiple as our direction vector, but looking at this question here, notice how they're asking us to use x of t equals -63t, which means they do want us to use a direction vector with an x component of -63. So we will use this direction vector, but if we had a choice, the greatest common factor of these components is 21. So if we did have a choice, we probably would use -1/21 times vector d as our direction vector, which would have an x component of 3, a y component of 1, and a z component of 7. But again, because of this question, we won't use this direction vector, we'll use this one. And now we have to find a point on the line of intersection of these two planes. Again, looking back at x of t equals -63t, because the constant here is 0, they want us to use a point where the x-coordinate would be 0. So I'll have to set up a system of equations to find the y and z components of this point of intersection. And again, we know we want to find a point with an x-coordinate of 0 because when we have parametric equations, x sub 1 would be the x-coordinate of a point the line passes through. So now if we know x is going to be 0, this would give us a system of equations. We'd have 3y minus 6z equals 15. In the second equation, we'd have -9y minus 3z equals -3. Let's solve this using elimination. Let's eliminate the y terms by multiplying this first equation by +3 and leaving the second equation the same. So we would have 9y minus 18z equals 45. Second equation stays the same. We add the equations to eliminate y. This gives us -21z equals, this would be 42, dividing both sides by a -21. We know the z-coordinate must be -2. So the z-coordinate must be -2, and I'll perform back substitution in order to find y. So notice if z is equal to -2, then we'd have, using the first equation, we'd have 3y. If z is -2, we'd have -6 times -2, that's +12, equals 15. Subtracting 12 on both sides, we have 3y equals 3, and therefore y equals 1. So we'll use this point to find the equation of the line of intersection. Let's go ahead and put these two pieces together on the next slide. Now that we have a direction vector and a point on the line, and we know we want to use a direction vector with an x-component of negative 63, we now know that a will equal negative 63, b will equal negative 21, and c will equal negative 147. And we also know x sub 1 will equal 0, y sub 1 will equal 1, and z sub 1 will equal negative 2. So writing all three parametric equations, we would have x of t equals, again, x sub 1 plus at, which would be 0 plus negative 63 times t, or negative 63t, which was given. Y of t would be equal to y sub 1 plus bt, which would be 1 minus 21t. And then z of t would be equal to z sub 1 plus c times t, or negative 2 minus 147t. So these are the parametric equations that our homework system wants us to use. But I do want to point out that it would have been simpler to use, instead of this direction vector, this scalar multiple, where we could let a equal 3, b equal 1, and c equal 7. So I do want to show that as well. If we use the direction vector, negative 1 over 21 times vector d would have had an x component of 3, a y component of 1, and a z component of 7, which would have given us the parametric equations x of t equals 0 plus 3t, or just 3t, y of t equals 1 plus 1t, or just 1 plus t, and z of t would be equal to negative 2 plus 7t. These parametric equations would give us the same line. It's just that our homework system did ask us to enter these parametric equations rather than these. And again, we just found the line of intersection of these two planes, which is graphed here in red. I hope you found this helpful.